We will now move on to simple and composite hypotheses. A simple hypothesis is a hypothesis that uniquely specifies the distribution of the population from which the sample is taken. A composite hypothesis is any hypothesis that is not a simple hypothesis. So we could consider a null hypothesis, theta equals theta 0, and that hypothesis would be simple as long as theta sub 0 specifies the distribution of the population. But the alternative, theta is greater than theta 0, would be composite because theta could be any number of values greater than theta 0, and so we do not uniquely specify the distribution. The alternative instead, that theta equals theta a specific alternative, would be simple. We could also consider random variables yn1 through yn coming from a normal distribution of mean mu, variance sigma squared. And the null hypothesis mu equals 5 would be simple, but only if sigma is known. It's composite if our standard deviation sigma is unknown, because we won't be able to uniquely specify the distribution just knowing that mu equals 5. So suppose we want to test two simple hypotheses. Those simple hypotheses would be theta equals theta 0 and a specific alternative, theta equals theta a. Then alpha, which we remember is the power of theta 0, is fixed. And that power of theta a is something that we want to be maximized. Our goal is to find a rejection region that maximizes that power. So what kind of rejection region should we choose? Well, we can consider one based on the Newman-Pearson lemma. The Newman-Pearson lemma says let y1, y2 through yn be a random sample from a distribution with parameter theta. And suppose that we wish to test the simple null hypothesis h0, theta equals theta 0, versus a simple alternative, ha, theta equals theta a. And then let L of theta be the likelihood of that sample. That's the likelihood function that we used previously. Then for a given alpha, the test that maximizes the power at theta a has a rejection region of the likelihood of theta 0 over the likelihood of theta a is less than k. And the value of k is chosen so that the test has a desired value for alpha. And such a test is a most powerful alpha level test for H0 versus HA. So this lemma gives us a form of a rejection region that's going to help us find the most powerful test for H0 versus HA given a specific alpha. So let's move on to an example. Consider a random variable y with density f of y is theta y to the theta minus 1, where y is between 0 and 1, and 0 elsewhere. And theta greater than 0 is unknown. We want to find the most powerful test with alpha equals 0.05 to test our hypothesis h0 is theta equals 2, and our alternative is theta equals 1. So in order to apply the Newman-Pearson lemma, we're going to need to do the ratio of two likelihoods, the likelihood of theta 0 over the likelihood of theta a. So remember, the likelihood would be, in this case, f of y given theta 0, since we only have that one parameter, theta 0. And then likelihood of theta a would be f of y given theta a. In this case, that's f of y given theta equals 2 over f of y given theta equals 1. Okay, so if theta is 2, then f of y is actually 2y to the first power. And if theta is 1, then f of y is actually just 1. And so the likelihood ratio in this case is 2y. So our rejection region, according to the lemma, should be that the likelihood ratio, in this case 2y, is less than k. Another way to write that is that y is less than k over 2. And we can think about that as y being less than some number we'll call k star. And our goal is to find k star so that our alpha is 0.05. So what is alpha in this case? Alpha is the probability that we're in the rejection region, y is less than k star. So the probability we reject the null hypothesis, given that it's true. In this case, theta is 2, is given that H0 is true. So what is that probability? Well, we have the probability density function, so we can integrate from 0 to k star, and we can integrate that likelihood, or likelihood ratio, we'll call that 2y dy. Of course, that integral would be k star squared, and we're going to set that equal to 0.05. So that tells us that k star is equal to the square root of 0.05. So if we choose a rejection region that y is less than the square root of 0.05, that maximizes the power of our test. One thing we might want to ask ourselves is, what is the corresponding maximum power in this case? Okay, so what is the power of the alternative theta sub a equals 1? Well, that's the probability that y is less than 0.05, but this time given theta is 1. Well, that's the integral from 0 to the square root of 0.05 of, well, now, because theta is 1, we have 1 here, dy, and that's equal to the square root of, well, the integral of 1 from 0 to square root of 0.05 is just the square root of 0.05. Okay, that number ends up being 0.2236. So the maximum power of this test is 0.2236 when theta is 1. So that is the most powerful test that we can run when alpha is 0.05. But what if we instead wanted to consider a different alternative? What if we wanted to consider the alternative theta equals 4? Then we would again have our likelihood ratio, the likelihood of theta of 0 over the likelihood of theta a. Okay, so that's f of y given theta 0 over f of y given theta a. So that's f of y given 2 over f of y given, in this case, 4. Okay, so we know that f of y given 2 was equal to 2y. Okay, but f of y given 4 is actually 4y cubed. Okay, this is theta is 4, and then y to the theta minus 1, which is 3. So we can reduce this down to 1 over 2y squared. Okay, that tells us that our rejection region is equal to when 1 over 2y squared is less than k, if we're applying the Newman-Pearson lemma. We can solve by multiplying by 2y squared. We get the 2y squared actually has to be greater than 1 over k, or in this case, then y has to be greater than the square root of 1 over 2k. So the form of the rejection region is, in this case, y is greater than k star. This is different than when theta was 1 and we had y is less than k star. So we must find k star such that alpha is 0.05. So alpha, just like before, is going to be the probability that y is bigger than k star, because that's our rejection region, given that theta equals 2, because that's our null hypothesis. That is a different integral, because we're going to do y greater than k star, so that's the integral from k star to 1 of 2y dy. Of course, the integral of 2y is y squared, so we're going to get 1 minus k star squared for that integral, and that has to be 0.05. Well, that tells us that k star squared is going to be 0.95, and so k star is the square root of 0.95. Okay, so our rejection region in this case is y greater than the square root of 0.95. Again, what is the power associated with that rejection region? So what is the power for the alternative theta equals 4? Well, that's the probability that y is less than 0.05, given that theta equals 4. That's going to be an integral from, y. Yes, that is the probability that y is less than, I apologize. That is the probability that y is greater than 0.95, given that theta equals 4. That's the probability that y is greater than square root of 0.95, given that theta equals 4. That's the square root of 0.95 to 1. That integral, we're going to integrate 4y cubed dy, because we're again given that theta equals 4, so the probability density function is 4y cubed in that case. If we work out that integral, we get y to the 4th. So that's 1 minus 0.95 square root of that to the 4th power. And that works out to be 0.0975. So that is the power of the test given, that is the power of the test given that theta is 4, and we have the rejection region that gives us the most powerful test. Okay, let's finish by finding the power function for the rejection region that we found. So the rejection region that we found in this last case was y is greater than the square root of 0.95. So we want to find the rejection, or we want to find the power function for that rejection region. Okay, so let's recall that that means that we're going to have a null hypothesis that theta is 2. And then I want to find the power function, so I'm going to consider all possible alternatives such that theta is greater than 2. In each of those cases, the power of theta sub a, okay, is the probability that y is greater than the square root of 0.95 given theta equals theta a. And just like the integral we had just done above, this will be the integral from the square root of 0.95 to 1 of theta a y to the theta a minus 1 dy. That integral is going to be y to the theta a. And it's going to go from the square root of 0.95 to 1. And so the answer is going to be 1 minus root 0.95 to the theta a power when theta a is greater than or equal to 0, and 0 when theta a is less than 0. Because that's not an alternative that we would be considering. So what does this look like? Well, first of all, let's make sure it matches with what we got before. See, the power is 1 minus 0.95 to the theta a. Notice above that the power was 1 minus 0.95, or root 0.95 to the fourth. Okay, so if we want to sketch the power function, then we'll notice that when theta is 2, the height is actually going to be 0.05. That's when theta equals theta 0. Right? That's what alpha is. And if we sketch that function, it'll look something like this, where we're looking at the power of theta a versus theta a. Now, the homework for this section is actually on a worksheet, and it asks you to do something similar to what we just did in the problem above.